All right, the final lab is actually two labs in one. It's kind of our CERTS lab. The production of N-butyl bromide and T-pentyl chloride. Two different labs in the same lab period. The reason why we did them together is that they are both substitution reactions, where we take alcohols and generate alkyl halides. That is, we are changing the OH for either a Br or a Cl. Okay? Because we're putting a halogen in place of the hydroxide, these are termed halogenation reactions. The specific type of reaction, that is the way it works, okay, depends on, number one, the substrate. Are we working with a primary, a secondary, or tertiary alcohol? They do different things. Okay? When that doesn't absolutely decide which way we're going to do that, then we look at what kind of nucleophile. We're using a strong nucleophile or a weak nucleophile that can help us decide. Okay. So N-butyl bromide, the production of, is an SN2, that is substitution by nucleophilic bimolecular mechanism. Okay. So our mechanism for that. Okay. Put an alcohol in an acidic environment and it will protonate. So the way to do that is to take the electrons, one of the unshared pair from the oxygen, and attach the proton to it. Now, if that were listed as hydronium, the hydrogen would accept a new bond and have to let go of the old bond. But we've given that to you as just hydrogen ion. Generates a protonated oxygen. Okay? That does a couple of things for us. Here again, if I wanted to break this bond and have the OH leave, it would be leaving as hydroxide, and that's quite basic. Now I can break this bond and have it leave as water. Water is less basic and so is a better leaving group. In addition, because this oxygen is positively charged, I make that, by inductive effects, the carbon that it's attached to even more slightly positive. That's now available. That's strongly positive enough so a fairly weak, stable ion like bromide can attack it. Here again, don't forget that carbon has two hydrogen as well, so it already has 4 bonds. As it accepts a new one, it has to let go of the old one, and that's the one to the positively charged oxygen. Now, this involves the generation of a transition state. In a transition state, we notice any bonds that are forming or breaking as dotted lines, okay? And it goes in brackets. These are very unstable, they're not around long, but generating it is the slow step. If you can get this transition state to make, then very quickly it will degrade or translate into the N-butyl bromide in water. Okay? Because this is the slow step, getting the bromide to attack and making the transition state. That requires both of the things, the reagents, to be present. That is why it's a bimolecular mechanism. Both the bromide and the alcohol concentration affect the rate of the reaction. The production of T-pentyl chloride, however, is an SN1. That is substitution by nucleophilic unimolecular mechanism. But here again, it's acid catalyzed. So we take an alcohol, we put it in the acid, and the same sort of thing is going to occur. Unshared pair from the oxygen, attack the proton. Here again, if that were hydronium, kick the bond to the oxygen out. Don't ever give hydrogen two bonds. So here again, we've made a better leaving group, and we've made the carbon that it's attached to more slightly positive. Okay? But because you have a couple of methyls and this ethyl on the other side, the chloride doesn't have room to get in at the carbon. It cannot attack the carbon, kicking the oxygen off. Okay? What happens though is eventually the oxygen gets tired of being positively charged, takes the electrons, and just leaves. Generating our carbocation intermediate. So here again, the SN2 with the primary alcohol resulted in a transition state. The SN1 with the tertiary alcohol results in an intermediate. Now I have a full +1 positive charged carbon, and it's sp2 hybridized. It went from sp3 here, being nice and constricted, to sp2, and now it's flat, and the chloride ion has plenty of room, top and bottom, to come in and attach. The slow step in this mechanism is right here, where the water has to decide to just pick up and leave. Notice that happens before the chloride plays any part in it. So the concentration of the alcohol will affect the rate of the reaction, but not the chloride. That's why only one of the reagents does, and hence the one designation for our term.